So, why do we use all these different schedulers? We have RMA, rate monotonic algorithm. We have earliest deadline first. We also have minimum laxity first. We have maximum urgency first. And of course, round robin schedulings, right? So what is it that we're trying to do with these? Well, first off, RMA is nice because it has schedulable guarantees. It doesn't require any special information. Think about it. The only thing you need to run your RMA scheduler is just a frequency you want to run it at, right? So there's not much information you really need to keep track of. And remember, it has this guarantee that your critical task set is always going to get scheduled, right? You always know exactly what's going to happen. And you have this deadline, this provable bound, that as long as you keep that, as long as you respect that boundary, no problems, okay? Now, but the drawback to the simplicity of RMA is, of course, that it doesn't make full 100% utilization of the CPU. That's where earliest deadline first comes in, is if you really want to get 100% of your CPU, then you have to use earliest deadline first, at least for your guarantees. Now, earliest deadline first, again, that's very simple. All it depends, because we assume that our deadlines are just a function of the period. And so we know all that information. So it's, if you have the same information you need for RMA, the period, you can use for EDF, and then you get 100% schedulable bound. The drawback is you don't know what's going to happen if there's a transient overload. Again, this gets into this case of practical firm real-time systems versus theoretical hard real-time systems. And so EDF, you just don't know which is going to fail, which is going to miss its deadline during transient overload, because dynamic priorities, it's based on what the deadline is, which again is the next period. Now, minimum laxity first, that is another dynamic scheduling algorithm that has a little bit more benefit, right? Especially during transient overload. But the problem with minimum laxity first is you have to know more information. It's a dynamic scheduling algorithm as well, but your operating system has to provide some additional information. Minimum laxity first has to know how long is it going to run, right? And because when we're trying to find the laxity, from the start point, right, to the completion point, we're going to look at how much time do we have left. And in order to do that, you have to know up front how much time you're expected to take. And so you have to know the execution time. Now, clearly, we've been using the execution time for these computations, of utility. So okay, but RMA, remember, doesn't need the utility to actually do the scheduling. It just has to know the frequency that it's running, at which it's running. So with minimum laxity first, you have that in, because what you're doing is you're saying, look, I have this much more to go, right? And I have look, I have this much more to go, but I have this much more time. So I can put my laxity becomes the difference between how much time before my deadline from now, right, and how I can fit it in there. If I have a little bit, oh, that's a lot more laxity, right? Than if I have a lot of time left, right? That's very small laxity. So minimum laxity goes first. This one gets preference over that one. Okay. Um, Now, that's where the MUF scheduler then comes in, the maximum urgency first. This is really a superset of all of these schedulers. That's what's kind of interesting about MUF, is MUF combines these capabilities of RMA, EDF, and MLF, minimum laxity first, earliest deadline first, rate monotonic, and puts all these together into a single algorithm, which also includes tiebreakers in terms of the user specified priority. Okay, so how does MUF work? Again, it's maximum urgency first, but the urgency consists of those three elements. There's the criticality, there's the laxity, and then there's the user priority. Um, and so think about it. The criticality is determined by rank ordering them in RMA order. So remember we said with MUF that that's a binary yes, no. It's either in the critical set or it's not in the critical set. However, if you use multiple bits to determine your criticality, in other words, you order them in RMA order, but you actually allow multiple values, okay? Well, that then is going to give you RMA scheduling, because that's what RMA order is. You rank them in order, you set the priority equal to it. So if you have a set of bits in your urgency, okay, your most significant bits are RMA ordering, well then they're going to dominate everything else. Okay, so you can have multiple bits. Suppose you set 8 bits to use, instead of just 1 bit, you set 8 bits to use or to specify criticality. Then that's going to behave exactly like RMA. Okay, now if you keep the criticality to 1 bit, and then you have your laxity goes next, you can, and then of course user priority, that's going to give you your MUF scheduling, where you set the criticality, either it's in the critical task set or it's not. And remember, the benefit of MUF was the critical task set, those were always going to run. Those can always make their deadlines, because that's the critical task set that where the worst case execution time, right, is always going to be 100%. So that's always schedulable. And remember, RMA will starve anything not in the critical task set in order to get the critical task set done. So with MUF, you know what is going to fail, right? It's things not in the critical task set. Critical task set will always execute, because again, you're assuming you'll never exceed your worst case execution bounds. Now, suppose we, oh, and there is a benefit that if there is time left over, right, you can still get 100% schedulable bound. So those tasks in the critical task set, again, if you have average performance leaves more time, you're going to have you're going to do the best you can to get those other tasks scheduled, as long as you have, until you've used up more than 100% of your CPU. Now, you can also set the criticality to always be 0. Okay, what that does is it turns off the RMA aspect, and the next most critical, because remember, the most significant bits are, but remember, right, the most significant bits are the ones that determine RMA order, whether that's 1 bit or multiple bits. The next set is your laxity measurement. Okay, the final set and least significant bits are the user priorities, right? So if you set that top bit to all zeros, you just zero out the criticality. Now, what you're doing is Muff will actually act as a minimum laxity first scheduler. Because remember, you assume you know now the execution time, and your operating system might actually be in real time generating that middle. If you basically zero out the criticality, now you get your minimum laxity scheduler. But wait a minute, if you turn off, if you just set all of your execution times to 0, well then what you're doing is you're setting that inside the next deadline. Well, if you set those all to 0, then it doesn't matter, right? Then you're back to an earliest deadline first algorithm. So Muff can also do, it can do RMA, it can do Muff, it can do minimum laxity first, and it can do EDF. Okay, all while if you set the priorities in the user priorities, you get tie-breaking capabilities. Now, how does this fit with round robin as well? So an example of a round robin scheduler is Arduino. Okay, our Arduino, or what also using ROS. ROS uses just a standard cue. It says pop whenever, it just sets a timer, and when the timer goes off, it's ready, and it just says, okay, try to execute whenever you can. So both ROS and Arduino are round robins. And that's why we say these are non-real-time systems. They have no sense of what's going on other than, oops, this task has to run. There's no prioritization other than first in, first out. And so that is how an example, and you get no guarantees at all, right? That even if there is a feasible schedule, either static or dynamic, round robin won't guarantee to find it. And that's why generally things like ROS and Arduino, while they're very useful, and I'm going to show you an example real quick, but they're very useful, there's no guarantee that you're going to meet your deadlines. Again, for firm systems though, it's very useful, and if you keep the system utilization down below, well below 70%, again, that's driven by the RMA, but it turns out it works pretty well for round robin also. Then you generally do pretty well, as I'm going to show just now.